First, we discuss what is the definition of partial differential equation. So, a differential equation which contains a known multivariable function and its partial derivative is known as the partial differential equation. So, basically, we know that there are two types of the differential equation. One is the ordinary differential equation and another is the partial differential equation. In ordinary differential equation, basically only one independent variable, and in partial differential equation more than one independent variable. As for example, first example, del square u by del x square plus del square u by del y square is equal to 0. This is the standard example which is called a two-dimensional Laplace equation where x and y is an independent variable and u is a dependent variable. The second one is a del square u by del t square is equal to c square del square u by del x square, which is called one-dimensional wave equation where x and t are independent variable and u is a dependent variable. And the another one, del u by del t is equal to c square del square u by del x square, which is called a one-dimensional heat equation where x and t is a independent variable. So first, what is the introduction of this concept, application of partial differential equation? So there are many engineering problems which, while the mathematical modeling result into an initial boundary value problem or boundary value problem. Therefore, we are applying there are different types of the method for solving the such type of problem. But we discuss only one method which is called a separable of variable method. Because separable of variable method is a powerful tool to solve initial boundary value problem or boundary value problem. When PD, that means partial differential equation, is a linear and the boundary conditions are homogeneous. So first we will discuss about the separation of variable method to such type of PD problems. So basically there are different types of problems arrive in a real world, and we convert any real world problem in a mathematics. That means we find the mathematical modeling of any real world problem which is convert in a partial differential equation with initial and boundary condition. And the problem is based in a linear, then we use a separable variable method. So first we discuss how to solve a problem of PD using the separable variable method. So the method is a separation of variable. So in this method, first we consider the solution uxy, where x and y are independent variable and u is a dependent variable. So again, in this method, first we consider uxy of a partial differential equation in the function u of two independent variable x and y as a product of a function of single variable. That means uxy is equal to capital X is a function of X, capital Y is a function of Y. That means any PD is given where X and Y is an independent variable and U is a dependent variable. We apply the separation of variable method. So first we consider a solution uxy which can be expressed as capital X of X, capital Y of Y. An advantage of this approach to find X and Y, as a solution of OD. That means using this approach, a PD is converted in a OD. And then after finding the solution of X and Y, we input here, then we get the solution of a given PDE. Now we discuss a separation of variable method in an example. So we take one example. Question is solve del u by del x plus del u by del y is equal to 0. Using a separation of variable methods. So in this partial differential equation, first we check which variable is a dependent and which variable are independent. So obviously here u is a dependent and x and y is a independent. So first we consider the solution form uxy is equal to capital X of X, Y of Y. So first we consider the solution uxy is equal to X of X, Y of Y. This is equation 1. Now we differentiate equation 1 with respect to X and Y because this is the solution of this equation. We consider obviously this is satisfied of this equation. So we find del u by del x and del u by del y. So we differentiate this equation with respect to x and differentiate this equation with respect to y. Then we get del u by del x is equal to x dash y constant and del u by del y is equal to x of x constant, y dash of y, where x dash of x means a first ordinary derivative dx upon dx and y dash of y is equal to d capital Y upon d small y, where capital X is a dependent of small x, y is a depends on a small y. Now we input both del u by del x and del u by del y in a equation 1. Then the given PD can be expressed, can be reduced to x dash of x, y of y plus x of x, y dash of y is equal to 0. So this implies x dash of x divided by x of x is equal to minus y dash of y upon y of y, which is considered equation 2. So from equation 2, the given PD become OD. So now this is a ordinary differential equation. This is also ordinary differential equation. It is also seen that a left hand side of equation 2, which is depends only on x, and in the right hand side, our differential equation is a depends only on y. And left hand side is equal to right hand side for all value of x and y. Therefore, we consider both side equal to the constant k. So we get two ordinary differential equation like x dash upon x is equal to k and minus y dash upon y is equal to k. So again I repeat, if we solve the first order PDE using the separable variable method, so here u is a dependent variable, x and y is an independent variable. So we write u of xy is equal to capital X of x, capital Y of y, where capital X of x, where capital X and capital Y is a function of small x and small y. Now differentiate with respect to x because you are required in an equation del u by del x, del u by del y. So we find del u by del x, del u by del y from equation 1 and then we input both value in a given equation, then we get this equation. And here we use the separable of variable method, then we separate both. X dash upon x is equal to x, x dash upon x is equal to minus y dash upon y. And then left hand side is equal to right hand side, we can consider is equal to constant k. So we get two ordinary differential equation. One is a x dash upon x is equal to k, and another equation minus y dash upon y is equal to k. Now we take first OD, x dash upon x is equal to k, where x dash is a function of x and x is also a function of x is equal to k. So implies x dash upon x, x dash is equal to kx is equal to 0. X dash is equal to kx. Therefore, x dash minus kx is equal to 0. And this is the first order ordinary differential equation. So we solve, we know that how to solve. So suppose we consider the auxiliary equation of this ordinary differential equation. So x dash we replace m minus k is equal to 0, so m is equal to k. So therefore the solution of first OD is x of x is equal to c1 e raised to kx. K is a real and different root. So therefore we write c1 e raised to kx. Similarly, we consider the second OD minus y dash upon y is equal to k. So that implies y dash plus ky is equal to 0. So the auxiliary equation is a m plus k is equal to 0. So m is equal to minus k. And again, minus k is a real and different root. And this is the first order OD. So we write the solution of the second OD is y of y is equal to c2 e raised to minus ky. So we solve first order OD, then we get x of x. We solve second order OD, then we get second order second OD, then we get y of y. And both input x of x and y of y in equation 1. That means this equation. So we get u of xy is equal to x of x, y of y is equal to c1 e raised to kx, c2 e raised to minus ky is equal to c1 into c2, both are constant, we consider c, so c into e raised to k x minus y. So u of xy is equal to c e raised to k x minus y is a solution of given first order PDE. Now we solve another example, but in the previous example we solved first order PD and this one is the second order PD. So example is solve a two-dimensional Laplace equation uxx plus uyy is equal to 0 using a separation of variable method. Procedure is similar, lightly changed, but initially are similar. So first, in this equation, u is a dependent variable, x and y is an independent variable. So we write u of xy is equal to capital X of x, capital Y of y. But here, this differential equation is not a first order, is a second order. Uxx, that means del square u by del x square. And uyy, that means del square u by del y square. So first we find del square u by del x square. That means we differentiate equation 1 with respect to x but 2 times. So we get uxx is equal to x double dash y. Similarly, equation 1 differentiate 2 times with respect to y, then uyy is equal to xy double dash. Where x double dash obviously second order ODE, y double dash is a second order ODE. Now we input uxx and uyy in a given equation 1. Then equation 1 is reduced to x double dash x y of y plus xy double dash is equal to 0. Now we separate both. So x double dash upon x is equal to minus y double dash or upon y. So again, from equation 2, the given PD become in a OD. It is also seen that the left hand side of the equation, which is depends only on x, right hand side equation is a depends only on y, and left hand side is equal to right hand side for all value of x and y. Then we consider the both side is equal to constant k. So we get 2 ODE like x double dash upon x is equal to k and minus y double dash upon y is equal to k. But equation 3 is not a first order ODE. It is a second order ODE. And we know that in a second order ODE, we consider is equal to k. So we can take the different value of k, then the solution of second order ODE is a different form. So for a second order ODE, we consider 3 different cases. First one is a k greater than 0, k less than 0, and k equal to 0. In each case, we find the solution of the given PD. So first we consider k greater than 0. So let us, one of the value which is always greater than 0, so we can take the square. That means a square, b square. Here we consider p square. So k is equal to p square is always greater than 0, where p not equal to 0. Then the given 2 ODE is obtained x double dash minus p square x is equal to 0 from equation 3. X double dash k is greater than 0. So x double dash upon x is equal to p square. Therefore, x double dash is equal to p square x. Therefore, x double dash minus p square x is equal to 0. Therefore, this is the second order ODE. So the auxiliary equation is m square minus p square is equal to 0. So m is equal to plus or minus p. M is equal to plus or minus p. That means real and different root. So we write x of x is equal to c1 e raised to px plus C2 e raised to minus px. Same procedure for the second OD. So we apply the same method. So the second OD is convert y double dash plus p square y is equal to 0. So the auxiliary equation is m square plus p square is 0. So implies m is equal to plus 1 minus pi. Now this is the complex root. So complex root, we know that the solution form is y of y is equal to C3 cos py plus C4 sin py. Because here real part is 0, imaginary part is p. So directly we write C3 cos py plus C4 sin py. Now the general solution of the given PD for case k greater than 0, we write uxy is equal to x of x, y of y. So x of x is this, c1 e raised to px plus c2 e raised to minus px, and y of y is a c3 cos py plus c4 sin py. Now we consider the second case, k less than 0. So in a k less than 0, we can take a one value which is always less than 0. So obviously minus p square, where p not equal to 0. So k is equal to minus p square is replaced in equation 3. Then equation 3 become x double dash plus p square x is equal to 0. And similarly, a second OD y double dash minus p square y is equal to 0. Now this is the second order OD. We apply the OD method. So auxiliary equation is m square plus p square is 0. So m is equal to plus 1 minus pi, complex root. Therefore x is equal to c1 cos px plus c2 sin px. In a similar way, here auxiliary equation is m square minus p square is equal to 0. So implies m is equal to plus 1 minus p. So this root is a real and different. So we write y of y is a c3 e raised to py plus c4 e raised to minus py. So therefore, the given PD solution for case k less than 0, we write uxy is equal to c1 cos px plus c2 sin px and c3 e raised to py plus c4 e raised to minus py. Now a third case, k equal to 0. So let k equal to 0, then a given 2 OD, that means equation 3 become x double dash is 0, y double dash is 0. So x double dash is 0, again second order OD. So we write m square is 0, auxiliary equation, so m is equal to 0 2 times. So the solution is a c1 plus c2x. Here m square is 0, then the solution is a c3 plus c4y. Now we combine both, then we get a solution of the given PD when k equal to 0, uxy is equal to c1 plus c2x, c3 plus c4y. So if the differential equation is a second order PD, then we consider a different case, k greater than 0, k less than 0, and k equal to 0. For each case, we find the solution of the given PD. So there are three different forms. There are three different solution form of the given PD. Now next topic, classification of PD of second order. Classification of PD of second order. So first, the general form of Cauchy-linear second order non-homogeneous PD can be written as A into del square u by del x square plus B into del square u by del x del y plus C into del square u by del y square plus D into del u by del x plus E into del u by del y plus F into u is equal to 0. So equation 1 is a second order Cauchy-linear non-homogeneous PD. Now this second order PD, how to classify? So we find the value of A, B, C, and the theory is equation 1 is said to be a elliptic if B square minus 4AC is less than 0. Equation 1 is said to be a hyperbolic if B square minus 4AC is greater than 0. And equation 1 is said to be a parabolic if B square minus 4AC is 0. That means any second order PD is given and we classify them, then we use the equation B square minus 4AC. We input the value of ABC in this equation. This is less than 0, so we can say the given PD is elliptic. If B square minus 4AC is greater than 0, then we can say the given PD is a hyperbolic, and equal to 0, then we can say the given PD is a parabolic. Now we discuss some example. So first example, here given that 5 into del square u by del x square plus 6 into del square u by del y square is equal to xy. Now we check this PD is which type, elliptic, parabolic, or hyperbolic. So obviously this equation we compare with the standard form, then we get A is equal to 5, B equal to 6, sorry, B equal to 0 because the term del square u upon del x del y here 0, so B equal to 0 and C equal to 6. So therefore we apply the equation B square minus 4AC. So B is 0, A is 5, B, C is a 6. So we get minus 120. That means less than 0. So therefore B square minus 4AC is less than 0. So we can say the given PD is a elliptic. In second example, here the coefficient of del square u by del t square, we can say A. So A is 1. Now this term we convert in a left hand, we transfer in a left hand side. So the equation is a del square u by del t square minus a c square del square u by del x square is equal to 0. So obviously A is 1. The middle term B equal to 0 and the last term C is equal to minus c square. So A is equal to 1. This is the mistake. B is 0 and C is equal to minus c square. C is equal to minus c square. So we apply the B square minus 4AC. So B is 0. A equal to 1. C is equal to minus c square. So we get B is equal to 0, C is equal to minus C square, A is equal to 1, so minus and minus C square, therefore plus 4AC square, 4C square, and this is also positive. So 4C square is greater than 0, then the given PD is a hyperbolic. So B is equal to 0, not minus C square, and C is equal to minus C square. Equation 3, A equal to C square, B is 0, C is 0. Because only one term, C square into del square U by del X square minus del U by del T is equal to 0. So A equal to C square, B equal to 0, C equal to 0. Therefore, B square minus 4AC is 0. Therefore, the given PD is a parabolic. And last, UXX plus UYY is equal to 0. So obviously A is equal to 1. The middle term, B equal to 0 and C equal to 1. So B square minus 4AC, B is equal to 0. A is 1, C is 1, so minus 4 which is less than 0. So again we can say the one dimension heat equation is elliptic. One dimension, two dimension Laplace equation is elliptic. One dimension heat equation is parabolic. And one dimension wave equation is a hyperbolic. Again, here mistake. This is not a one dimension heat equation. This is a two dimension Laplace equation. So two dimension Laplace equation is a elliptic. One dimension heat equation is parabolic, and one dimension wave equation is a hyperbolic. Now, thank you. Now we discuss a one dimension heat equation and its example with the initial and boundary value problem in lecture 2.